What's up guys, my name is Ritvik and today I'm here to teach you everything that you need to know about AP Calculus AB and BC Unit 8. Now before I begin, please go to the description right now and get my free AP Calculus AB and BC books because those books have everything that you need to know to get a 5 and an A in your class. So what are you waiting for? Get it right now, and now let's begin immediately with the video. So Unit 8 starts with the average value of a function, and the average value of a function f of x from the interval from a to b is 1 over b minus a times the integral of f of x from a to b. And the reason is that the average value of a function involves you to add up each possible value of that function in that interval. So for example, if my interval is from 1 to 2, then I want to find f of 1 plus f of 1.00001. I want to find each specific value. And to do that, I integrate, because when I integrate, I can find the sum of all possible values. And then I divide by b minus a, which is the length of the interval. Now let's look at an example. Now this yellow area that you see, that's the sum of all possible values for this function f of x equals to x squared from minus 3 to positive 3. Now the average value can be represented as 1 over 6 times the integral of negative 3 to 3 of f of x. And then since f of x equals to x squared, let's actually find the integral. So when we integrate x squared, we get x cubed over 3. And then we evaluate that from negative 3 to 3. So we can proceed to find that the average value is 3. Now let's connect position, velocity, and acceleration again. I want to remind you of this topic again. So the integral of acceleration with respect to time is velocity. The integral of velocity with respect to time is the position. Now it's important to know the key difference between displacement and distance. To find the displacement or the change in position, you can simply integrate velocity. But if a problem asks you to find the total distance, then you must integrate the absolute value of velocity. Now, let's find the area between curves with respect to x. So first, you'll be given two curves, and then your goal will be to draw both of the curves, and then see which one lies above the other. And then you find the intersection points to find your integration bounds. And then you imagine an infinite number of thin vertical strips between the area. And then you notice that you can find the area of each vertical strip, and then you can integrate with respect to x to find the total area between the curves. Let's look at an example. So this red curve that you see is f of x equals to x squared, and the green one is the function of just x, so y equals to x. So now these rectangles that you see, that represents the area between the curve. But the more the rectangles you have, the more accurate the area will be. And that's when you integrate to find the area between the curves. So you simply subtract the two functions and then integrate using your integration bounds. So in this problem, right, f of x is x and g of x is x squared. And we're integrating from 0 to 1. So the difference between the two functions is just x minus x squared. So we can integrate to get x squared minus x cubed over 3. And then we use the bounds to get an answer of 2 over 3. Now area between curves with respect to y. The process is similar. You first draw out both of the functions, see which one lies to the left or to the right, and then you find the intersection points to find your integration bounds. And in some problems, you'll be given the integration bounds, so you can just use that simply. And then you imagine an infinite number of thin horizontal strips. And then the area can be represented as f of y minus g of y, which is the difference between the two functions, times dy, which is like the infinitely small width, and then you can integrate that. Now finding the area between curves that intersect at more than 2 points. So to do this, you simply set up multiple integrals. So first you find all the intersection points, and then you can make multiple integrals. So one from the first intersection point to the second one, and then a second integral from the second intersection point to the third intersection point. And then you can evaluate each integral separately. Now volumes with cross sections, squares, and rectangles. So now we will have cross sections perpendicular to either the x or the y-axis. Now we will be making an infinite number of cross sections such as squares or rectangles, and then that will create a volume for that figure. So basically, the base of the rectangle or the base of the square, right, that will simply be the difference between the two functions that you graph out. So if, for example, if we have two functions, f of x and g of x, and then we have cross sections perpendicular to it of squares, then the base of each square will be f of x minus g of x, and then the height will also be f of x minus g of x. And for a rectangle, you usually be given a ratio between the base and the height. For example, the height is 2 times the base. So if the base is f of x minus g of x, then the rectangle's height will be 2 times f of x minus g of x. So now let's look at a very good animation. So for this function, right, I'm going to be showing you how cross sections perpendicular to the x-axis look like and what the volume will look like. Please closely view this animation. So this might look like a rectangle, but it's actually a square, and the reason is that it's scaled like that, so it looks like a rectangle, but it's not. Now I hope you like the animation. For a rectangle, I'm going to give you an example. So if the base is f of x minus g of x and the height is 2 times f of x minus g of x, then the area of this cross section can be represented as 2 times f of x minus g of x squared. So, and then the depth of each cross section, or like the width of it, is dx. So we can multiply that to find the volume of each cross section, and then we can simply integrate this from a to b, our integration bounds, to find the total volume. Now volumes with cross sections, triangles, and semicircles. Now the process is the same. However, the area for each cross section will be different. For example, for a triangle, it might be a right triangle, so you have to count for that. And for a semicircle, if you have semicircles perpendicular to the x-axis, and the difference between the two functions is f of x minus g of x, then the radius will be half of that, which is f of x minus g of x over 2. So pi times that expression squared divided by 2, because it's a semicircle. So the area of a semicircle is half the area of a circle. So it's important to have some practice with this. So if you want to go deeper, check out my book. And the book is linked in the description. Now volume with disk methods, revolving around the x or y-axis. Now this is super important. Now when we rotate a function, notice that there will be an infinite number of vertical or horizontal strips, super thin ones. So basically you have to visualize rotating each strip, and then you can get a disk with thickness dx or dy. So if you're rotating around the x-axis, the thickness will be dx, and if you're rotating around the y-axis, the thickness will be dy. So basically try to visualize it, and I'll be showing you an animation to help you visualize it. So look at this function. I want to rotate this function from 1 to 3 around the x-axis. Look at how it's done. So basically I simply bring this area around the entire x-axis. And then the region that it sweeps out, that represents the volume. So this is how the volume looks like. Now to find the volume of this, we can notice that there's an infinite number of disks that make up this volume. So since there's an infinite number of disks, let's say that this function is f of x, right? Then for a specific point x, right, then the radius of that disk will be f of x. So that means the area of one cross section of one disk will be pi times f of x squared. And then we can integrate that using our integration bounds with dx to find the volume. Don't worry if it's confusing right now, there's going to be plenty of examples towards the end to clear this out for you. Now sometimes the axis of rotation is different. It's not always going to be the x and the y axis. So now you simply find the difference between the function and the new axis of rotation, and then you will still write an equation, a general equation for the area of each circular disk, and then integrate with respect to x if you're revolving around an axis that's parallel to the x-axis, or integrate with respect to y if you're revolving around an axis that's parallel to the y-axis. Now volume with washer methods. Now instead of just rotating one function, you will rotate the area between two functions. The cross section will create a circle inside a circle, and that's known as a washer. Now to find the volume using washers, you will first find the area of the large circle minus the area of the small circle. So you'll find an expression for the area of a washer, and then you can integrate using that. Let's look at an animation. So this is the two functions, y equals x and y equals 2x squared. And I want to rotate these two functions around the x-axis. And then I want to find the volume that it sweeps out. So I just want to show you the visualization so you can actually visualize how this works. So these moving circles, right? Both of them combined make the washers. Now I want to show you volumes using the washer methods when you revolve around a different axis. So basically, now the outer radius and the inner radius of the circle will be a little different since the axis of rotation is different. And then you can account for that difference by finding the area of the large circle and the area of the small circle. So basically, you will have new radius, right? So if my function y equals to f of x, if that's my function, right? And I have another function y equals to g of x, and then I'm rotating around the axis y equals to 2. Then one of the radiuses will be f of x minus 2 because I find the difference between that function, and then the other radius will be g of x minus 2. And don't worry if this is confusing. Again, there's going to be examples at the end to show it and help you visualize this more. So now look at this. I'm rotating the area between y equals to x and y equals to x squared now around a different axis of rotation. So the only thing that changes is the radius of the outer and the inner circle of the washer. Now the arc length of a smooth planar curve and distance traveled. So if we have a function y equals to f of x that is continuous for an interval from a to b, then the arc length for that interval is the integral from a to b of the square root of 1 plus f prime of x squared with respect to x. So in general, just memorize this formula. There's no point of trying to derive it on your own. Please memorize it. It's going to make your life extremely easy. Now let's look at a free response question from the actual AP exam. So we have a shaded region R that is bounded by the curves xy equals to 1, x equals to 1, x equals to 2, and y equals to 0. In part A, we want to find the volume of the solid figure that's generated by revolving the region R about the x-axis. And then in part B, we want to find the volume of the region, of this region R, when we rotate it around the line y equals to -2. So please pause the video and try the problem on your own before you proceed. So by now I hope you actually pause the video to try the problem. So let's look at the solution. So first step, draw the area of the region that we're given. So the region R, we first draw the curve xy equals to 1, and then we draw x equals to 1 and x equals to 2. And then we can see that the area looks like this. So basically, let's make many thin, infinite number of vertical strips. This will allow us to visualize how I'm finding the volume. So now, if we rotate this entire region around the x-axis, let's think about what would happen if we just rotate one extremely thin vertical strip. Well, if we simply rotate it around the x-axis, right, we're going to get like a circle known as a disk. And now this circle will have a radius of y equals to 1 over x because our function is xy equals to 1 and it's bounded by the x-axis. So that's why the height of each vertical strip, right, or the radius is y equals to 1 over x. And now if you rotate this around the x-axis, then the area will be pi times r squared, where r is the radius, which is 1 over x. So we get pi times 1 over x squared. And then we're doing this for all the disks from x equals to 1 to x equals to 2, which is the integration bounds. So pi times 1 over x squared is pi over x squared, and then we can integrate this to get pi times minus 1 over x from 1 to 2. And then we can evaluate this to get. Now for part B, we have the same region again, right? The same region R. However, now we're rotating this around y equals to -2. So things are going to be a little different. Now to find the volume that this region specifically sweeps out, we must notice that now we have an outer radius and an inner radius. So the outer radius will simply be this y equals to 1 over x, right? That was the original radius. However, now we're rotating around y equals to -2. So it's 1 over x plus 2. And then the inner radius will simply be the distance between the x-axis and y equals to -2, which is 2. So that's the inner radius. It's going to be constant, while the outer radius will be 1 over x plus 2. So that means the area of one washer will be pi times 2 plus 1 over x squared minus 2 squared. And this simplifies to pi times 1 over x squared plus 2 over x. And then we can integrate this from 1 to 2 to find that the total volume is pi over 2 plus 2 pi times the natural log of 2. Now let's look at another free response question. So please pause the video, read the problem, and try it on your own. So now in this problem, we have a region R in the first quadrant enclosed by this circle, x squared plus y squared equals to 9, the x-axis, and x equals to 0, and x equals to 3. And in part A, we want to find the volume of this solid when this region is revolved around the x-axis. So again, first step, you draw the curve that we have. So this is the curve that we have. And then these are thin vertical strips that I'm drawing out so I can help you visualize how this works. So again, I'm going to be, instead of rotating the entire region around, let's look at what would happen if I rotate an extremely thin vertical strip or vertical rectangle. So if I rotate an extremely thin strip, it's going to create a disc or a circle. And that disc will have a radius, so I can find the area using pi r squared. Now since my function is x squared plus y squared equals to 9, I can rearrange the equation to get y squared equals to 9 minus x squared, which is the square root of 9 minus x squared. And then that means my radius is the square root of 9 minus x squared. So I can square that, multiply by pi to find that the area of a general cross section is pi times 9 minus x squared. And now I can integrate this from 0 to 3. And then after I do that, I can find that the total volume is 18 pi. Now in part B, we want to set up an integral for what happens when we rotate this region R around the line y equals to minus 2. So the volume of the solid when we do that. Well, so now our new axis of rotation is y equals to minus 2. So we're going to have an inner radius and an outer radius because we're rotating that same region R. So we already found that the radius was y equals to the square root of 9 minus x squared. However, now this function that we have is being rotated around y equals to minus 2. And that means that we must add 2 to the y equals to the square root of 9 minus x squared to find our outer radius. And then the inner radius is simply 2. So that means the area of a washer in general for this problem will be the pi times the square root of 9 minus x squared plus 2, which is the outer radius, squared, minus 2, which is the inner radius, squared. And that's the area, and now this is the expression for the volume. Now thank you so much for watching this video, and please don't forget to like, share, and subscribe, since that's going to tell me that you guys are truly enjoying and learning from the books and the videos that I've been making for you guys. And don't forget to join the Discord server to meet other hardworking students that are preparing for various competitions and exams such as the AP exams. And also, don't forget to follow the Instagram if you have Instagram to view educational reels and cool animations. And again, thank you so much for watching this video, and I really hope to see you soon back again on this channel.